Hello, my dear students and the rest of the learners. Welcome to this presentation in which we are going to discuss on the topic device input-output management. This is part 5 of a 5-part series of presentations and videos in the topic device input-output management in operating systems. The title of this presentation is Computer Clock System, Computer Terminals, and Visual Devices. My name is Meme JM, or you can simply call me Emily Swap. In this presentation, or the content of this presentation is on computer clock system, the computer terminals, and the visual devices. Let's commence by looking at computer clocking system. Clocks, also called timers, are essential to the operation of any multi-programmed system for a variety of reasons. They maintain the time of day and prevent one process from monopolizing the CPU. Therefore, most computers have hardware clocks and timers that provide 3 basic functions. These are, number 1, they give the current time. Number 2, they give the elapsed time. And number 3, they set a timer to trigger an operation at a certain time. These functions are used heavily by the operating system and also by time-sensitive applications. The hardware to measure elapsed time and to trigger operations is called a programmable interval timer. The clock task has some resemblance to a device driver in that it is driven by interrupts that are generated by a hardware device. However, the clock is neither a block device like a disk, nor is it a character device like a terminal. These functions are used heavily by the operating system and also by time-sensitive applications. The hardware to measure elapsed time and to trigger operations is called a programmable interval timer. The clock task has some resemblance to a device driver in that it is driven by interrupts generated by a hardware device. However, the clock is neither a block device like a disk, nor a character device like a terminal. The clock task executes in kernel space and cannot be accessed directly by user space processes. It has access to all kernel functions and data, but user space processes can only access it via the system task. Let us now look at the clock hardware. All the clock hardware does is generate interrupts at known intervals. The 2 types of clock or clocks that are commonly used in computers are both quite different from the clocks and watches that are used by people. The simpler clocks are assigned to the 110 or 220 volt power line, and they cause an interrupt on every voltage cycle at 50 or 60 Hz. These clocks used to dominate, but are rare nowadays. The other kind of clock is built out of 3 components, which are a crystal oscillator, a counter, and a holding register. When a piece of quartz crystal is properly cut and mounted under tension, it can be made to generate a periodic signal of very great accuracy, typically in the range of several 100 megahertz depending on the crystal that is chosen. Using electronics, this basic signal can be multiplied by a small integer to get the frequencies up to 1000 megahertz or even more. At least one such circuit is usually found in any computer, providing a synchronizing signal to the computer's various circuits. This signal is fed into the counter to make it count down to 0. When the counter gets to 0, it causes a CPU interrupt. Programmable clocks operation. In one short mode, when the clock is started, it copies the value of the holding register into the counter and then decrements the counter at each pulse from the crystal. When the counter gets to 0, it causes an interrupt and stops until it is explicitly started again by the software. In square wave mode, after getting to 0 and causing the interrupt, the holding register is automatically copied into the counter and the whole process is repeated again indefinitely. These periodic interrupts are called clock ticks. The advantage of the programmable clock is that its interrupt frequency can be controlled by software. Programmable clock chips usually contain 2 or 3 independently programmable clocks and have many other options as well. For example, counting up instead of counting down, interrupts disabled, and more. To prevent the current time from being lost when the computer's power is turned off, most computers have a battery-powered backup clock that is implemented with the kind of low power circuitry that is used in digital watches. The battery clock can be rent at the startup. If the backup clock is not present, the software may ask the user for the current date and time. There is also a standard way for a networked system to get the current time from a remote host. At every clock tick, the real time is incremented by 1 count. Usually, utility programs are provided to manually set the system clock and the backup clock and to synchronize the 2 clocks. We should mention here that all but the earliest IBM compatible computers have a separate clock circuit that provides timing signals for the CPU, internal data buses, and other components. This is the clock that is meant when people speak of CPU on the earliest personal computers and in gigahertz on the modern systems. The basic circuitry of quasi crystals, oscillators, and counters is the same, but the requirements are so different that modern computers have independent clocks for CPU control and timekeeping. Let's now look at clock software. The clock software can take the form of a device driver and can thus be called the clock driver. The exact duties or functions of the clock driver vary among operating systems, but usually include most of the following. Number 1 is maintaining the time of day, which is also called the real time. It just requires incrementing a counter at each clock tick. The only thing to watch out for is the number of bits in the time of day counter. With a clock rate of 60 Hz, a 32-bit counter will overflow in just over 2 years. 3 approaches can be taken to solve this problem. The first way is to use a 64-bit counter although doing so makes maintaining the counter more expensive since it has to be done many times a second. The second way is to maintain the time of day in seconds rather than in ticks, using a subsidiary counter to count the ticks until a whole second has been accumulated. Because 232 seconds is more than 136 years, this method will work until well into the 22nd century. The third approach is to count the ticks, but to do that relative to the time the system was booted rather than relative to a fixed external moment. When the backup clock is read or the user types in the real time, the system booted time is calculated from the current time of day value and stored in memory in any convenient form. When the time of day is requested, the stored time of day is added to the counter in order to get the current time of day. Number 2 is preventing processes from running longer than they are allowed to. Whenever a process is started, the scheduler initializes a counter to the value of that process's quantum in clock ticks. At every clock interrupt, the clock driver decrements the quantum counter by 1. When it gets to 0, the clock driver calls the scheduler in order to set up another process. Number 3 is accounting for CPU usage. The most accurate way to do it is to start a second timer that is distinct from the main system timer whenever a process is started. When that process is stopped, the timer can be read out to tell how long the process has run. To do things right, the second timer should be saved when an interrupt occurs and restored afterwards. Number 4 is handling the alarm system call that is made by user processes. In many systems, a process can request that the operating system give it a warning after a certain interval. The warning is usually a signal, an interrupt, a message, or something that is similar. One application requiring such warnings is networking, in which a packet not acknowledged within a certain time interval must be retransmitted. Another application is computer-aided instruction, where a student not providing a response within a certain time is told the answer. If the clock driver had enough clocks, it could set a separate clock for each request. This not being the case, it must simulate multiple virtual clocks with a single physical clock. One way is to maintain a table in which the signal time for all pending timers is kept, as well as a variable giving the time of the next one. Whenever the time of day is updated, the driver checks to see if the closest signal has occurred. If it has, the table is searched for the next one to occur. Number 5 is providing watchdog timers for parts of the system itself. Parts of the operating system also need to set timers. These are called watchdog timers. The mechanism that is used by the clock driver to handle watchdog timers is the same as for user signals. The only difference is that when a timer goes off, instead of causing a signal, the clock driver calls a procedure that is supplied by the caller. The procedure is part of the caller's code. The code procedure can do whatever is necessary, even causing an interrupt. Although within the kernel interrupts are often inconvenient, and the signals do not exist. That is why a watchdog mechanism is provided. It is worth noting that the watchdog mechanism works only when the clock driver and the procedure to be called are in the same address space. Number 6 is doing profiling, monitoring, and statistics gathering. Some operating systems provide a mechanism by which a user program can have the system build up a histogram of its program counter so that it can see where it is spending its time. When profiling is a possibility, at every tick the driver checks to see if the current process is being profiled, and if so, computes the bin number, that is, a range of addresses corresponding to the current program counter. It then increments that bin by 1. This mechanism can also be used to profile the system itself. Most computers have a second programmable clock, which is called soft timers, that can be set to cause timer interrupts at whatever rate a program needs. This timer is in addition to the main system timer, whose functions have already been described above. As long as the interrupt frequency is low, there is no problem using this second timer for application-specific purposes. The trouble arrives when the frequency of the application-specific timer is very high. Soft timers avoid interrupts. Instead, whenever the kernel is running for some other reason, just before it returns to user mode, it checks the real-time clock to see if a soft timer has expired. If the timer has expired, the scheduled event, for example, a packet transmission or checking for an incoming packet, is performed with no need to switch into kernel mode since the system is already there. After the work has been performed, the soft timer is reset to go off again. All that has to be done is copy the current clock value to the timer and add the timeout interval to it. Soft timers stand or fall within the rate at which the kernel entries are made for other reasons. These reasons include system calls, TLB misses, page faults, I/O interrupts, and the CPU going idle. Let's now focus on computer terminals. A computer terminal is an electronic or electromechanical hardware device that is used for entering data into and displaying data from a computer or a computing system. Early terminals were inexpensive devices, but very slow compared to punch tickers or paper tape for input. But as the technology improved and the video displays were introduced, terminals pushed these older forms of interaction from the industry. A related development was time-sharing systems, which evolved in parallel and made up for any inefficiencies of the user's typing ability with the ability to support multiple users on the same machine, each at their own terminal. The function of a terminal is confined to display and input of data. A device with significant local programmable data processing capability may be called a smart terminal or a fat client. A terminal that depends on the host computer for its processing power is called a thin client. A personal computer can run software that emulates the function of a terminal, sometimes allowing concurrent use of local programs and access to a distant terminal host system. Historically, terminals have come in a variety of forms. It is up to the terminal driver to hide all these differences so that the device-independent part of the operating system and the user programs do not have to be rewritten for each kind of terminal. A text terminal, or often just a terminal, sometimes text console, is a serial computer interface for text entry and display. Information is presented as an array of pre-selected formed characters. When such devices use a video display, such as cathode ray tube, they are called a video display unit or visual display unit, VDU, or video display terminal, VDT. What is terminal hardware? From the operating system's point of view, terminals can be divided into three broad categories based on how the operating system communicates with them, as well as their actual hardware characteristics. These are, number one, memory-mapped interface terminals. These consist of a keyboard and a display, both of which are hardwired to the computer. This model is used in all personal computers for the keyboard and the monitor. RS232 interface terminals is the second one. These terminals consist of terminals that interface via a serial communication line using the RS232 standard, most frequently over a modem. This model is still used on some mainframes, but PCs also have serial line interfaces. Network interface terminals. This consists of terminals that are connected to the computer via a network. These types of terminals, which we also call taxonomy, can be illustrated as follows. From this diagram, my dear students and the rest of the learners, you can see that generally terminals are categorized into three. These are the memory mapped interface, the RS232 interface, and the network interface. Then the memory mapped interface can be subdivided into two, where we have the character oriented and the bit oriented. The RS232 interface entails the glass TTY and the intelligent terminal, while the network interface entails the X terminal. What is a memory mapped terminal? These are terminals that are usually integral parts of the computers themselves, especially personal computers. They consist of a display and a keyboard. Memory mapped displays. Memory mapped displays are interfaced via a special memory that is called a video RAM, which forms part of the computer's address space and is addressed by the CPU in the same way as the rest of memory. Therefore, the CPU writes data to a special memory that is called video RAM. The video controller reads the characters from the video RAM and then it displays them. These terminals can be diagrammatically represented as follows. From this diagram, my dear students and the rest of the learners, you can see that we have a bus through which the CPU, memory, and the video RAM card are connected. And the video card RAM also contains what we call the video controller that is in charge of controlling and communicating with the monitor. And therefore, an analog video signal is sent between the video RAM card's video controller and the monitor for the purposes of displaying the required information. Then On the same note, we have a keyboard which is connected to a parallel port, and this port is also connected with the bus. Also, on the video RAM card, just as I have said, is a chip that is called a video controller. This chip pulls bytes out of the video RAM and generates the video signal that is used to drive the display. Displays are usually one of two types, that is, the carbon ray tube monitors or flat panel displays. These days, the CRT monitors are getting phased out and replaced by the flat panel displays. The video controller signal modulates the intensity of the electron beam, determining whether a given pixel will be light or dark. The original IBM PC had several modes for the screen. In the simplest one, it used a character mapped display for the console. With a memory mapped display, the keyboard is completely decoupled from the screen. It may be interfaced via a serial or a parallel port. On every key action, the CPU is interrupted and the keyboard driver extracts the character typed by reading an I/O port. On a PC, the keyboard contains an embedded microprocessor which communicates through a specialized serial port with a controller chip on the mainboard. An interrupt is generated whenever a key is struck and also when one is released. Let's now focus on RS232 terminals. That is number 2. These are devices containing a keyboard and a display that communicates using a serial interface 1 bit at a time. These terminals use a 9-pin or a 25-pin connector, of which 1 pin is used for transmitting data, 1 pin is for receiving data, and 1 pin is ground. The other pins are for various control functions, most of which are not used. To send a character to an RS232 terminal, the computer must transmit it 1 bit at a time, prefixed by a start bit and followed by a 1 or 2 stop bits to delimit the character. A parity bit, which provides rudimentary error detection, may also be inserted preceding the stop bits, although this is commonly required only for communication with mainframe systems. These terminals are commonly used to communicate with a remote computer using a modem and a telephone line. The following diagram illustrates this type of terminal. From this diagram, it is very clear that we have a computer and we also have a terminal. This terminal contains UART, which is connected by a receiving line as well as transmitting line to RS232 interface card through the UART. Inside the computer, we have the central processing unit, the memory, as well as the interface card that are all interfaced together or connected together to a bus. Since both computers and terminals work internally with the whole characters, but must communicate over a serial line a bit at a time, chips have been developed to do the character to serial and serial to character conversions. They are called UARTs, which stands for Universal Asynchronous Receiver Transmitters. Universal Asynchronous Receiver Transmitters. The Universal asynchronous receiver transmitters are attached to the computer by plugging RS232 interface cards into the bus. On modern computers, the UART and RS232 interface is frequently part of the parent board chipset. It may be possible to disable the onboard UART in order to allow use of a modem interface card plugged into the bus, or two of them may be able to coexist. A modem also provides a UART, although it may be integrated with other functions in a multi-purpose chip, and the communication channel is a telephone line rather than a serial cable. To print a character, the terminal driver writes the character to the interface card where it is buffered and then shifted out over the serial line 1 bit at a time by the UART. As a result of this slow transmission rate, the driver generally outputs a character to the RS232 card and blocks, waiting for the interrupt generated by the interface when the character has been transmitted and the UART is able to accept another character. The UART can simultaneously send and receive characters, as its name implies. An interrupt is also generated when a character is received, and usually a small number of input characters can be buffered. The terminal driver must check a register when an interrupt is received in order to determine the cause of the interrupt. Some interface cards have a CPU and memory and can handle multiple lines, taking over much of the I/O load from the main CPU. RS232 terminals can be subdivided into 3 categories. These are, number 1, hand copy or printing terminals. Characters typed on the keyboard were transmitted to the computer. Characters sent by the computer were typed on the paper. These terminals are obsolete and rarely seen anymore. The second category of RS232 terminal is the dump CRT terminals. These are terminals that can interpret a limited number of control codes, but do not have the ability to process special escape sequences that they perform. It is any type of traditional computer terminal that communicates serially over RS232 connection that does not locally process data or execute user programs. It can also refer to a public computer terminal that is limited to monochrome text-only capabilities, or to terminals that transmit rather than waiting until it is polled by a host computer. These work like the hand copy terminals, but with a screen instead of paper. They are frequently called glass TTYs because they are functionally the same as hand copy TTYs. The term TTY is an abbreviation for teletype. Glass TTYs are also obsolete. Number 3 is intelligent CRT terminals. These are in fact miniature specialized computers. They have a CPU and memory and contain software, usually in ROM. From the operating system's viewpoint, the main difference between a glass TTY and an intelligent terminal is that the latter understands certain escape sequences. These were called intelligent or smart because they had the capability of interpreting escape sequences in order to position the cursor and control the display. Number 3 is network interface terminals. These are terminals that are used to connect a remote user to computer over a network, either a local area network or a wide area network. There are two different philosophies or views of how network terminals should work. Number 1, the terminal should have a large amount of computing power and memory in order to run complex protocols to compress the amount of data sent over the network. For example, X terminal. A protocol is a set of requests and responses that a sender and receiver agree upon in order to communicate over a network or other interface. Number 2 is the terminal should be extremely simple, basically displaying pixels and not doing much thinking in order to make it very cheap. An example is the minimal slim terminal. So what is X terminal? The ultimate in intelligent terminals is a terminal that contains a CPU as powerful as the main computer, along with megabytes of memory, a keyboard, and a mouse. One terminal of this type is the X terminal, which runs the X window system that is often just called X. An X terminal is a computer that runs the X software and which interacts with the programs running on a remote computer. The program inside the X terminal that collects input from the keyboard or a mouse and accepts commands from a remote computer is called the X server. It has to keep track of which window is currently selected, where the mouse pointer is, so it knows which client to send any new keyboard input to. It communicates over the network with X clients running on some remote host. It sends them keyboard and mouse input and accepts display commands from them. It may seem strange to have the X server inside the terminal and the clients on the remote host, but the X server's job is to display bits, so it makes a sense to be near the user. From the program's point of view, it is a client telling the server to do things like display text and geometric figures. The server in the terminal just does what it is told to do, as all servers do. It is also possible to run the X window system on top of Unix or another operating system. What the X window system really defines is the protocol between the X client and the X server. It does not matter whether the client and the server are on the same machine or spread apart. The following diagram illustrates an X interface terminal. From this diagram, my dear students, and the rest of the learners, you can see that on one side, we have a remote host, and on the other side, we have an X terminal. This X terminal is simply a monitor, a keyboard, and a mouse that have been connected together to an X server, which is served by Unix. And of course, we have the hardware. On the remote host side, we have the content of the user space and the content of the kernel space. Under the user space, we have the window manager and application program. Then below it, we have motif, in36, xlib, xclient, Unix, and then that is under kernel space, we have Unix and hardware. These two, the remote host and the X terminal, all are guided by what we call the X protocol. And when the two are connected together, they are, of course, forming a network, or they are a part of a network. When an X program starts, it opens a connection to one or more X servers. Let us call them workstations, even though they might be located on the same machine as the X program itself. X considers this connection to be reliable in the sense that lost and duplicate messages are handled by the networking software, and it does not have to worry about communication errors. A key concept in X is the resource. A resource is a data structure that holds certain information. Application programs create resources on workstations. Resources can be shared among multiple processes on the workstation. Resources tend to be short-lived and do not survive workstation reboots. Let's now focus on Slim Network Terminal. That is number 2. Slim stands for Stateless Low-Level Interface Machine. This is a high-performance interactive computing terminal that is composed of a display with a keyboard and a mouse, but with no user installable software. The idea is based on traditional centralized time sharing. Terminals that have little processing capacity are called thin clients. The following diagram illustrates a slim terminal system. From this diagram, we can see we have the computer center, which consists of disks. We have server or servers that are connected through a switch to the clients. And therefore, the clients, for example, the thin client is connected to a switch using dedicated network connection, and then from the switch, or that is then interconnected to the servers through the switch. Let us now focus on terminal software. This is the software, mostly the drivers, that enable each of the devices in a terminal to function appropriately. The software that enables the input devices of a terminal to operate is called the terminal input software. Example is keyboard drivers, while that which makes the output parts of a terminal to function are called the output terminal software. An example is video controller drivers. This software is named based on the type of terminal that it operates. For example, memory mapped terminal drivers, RS232 terminal drivers, amongst others. For an application, the simplest way to use a terminal is to simply write and read text strings to and from it sequentially. The output text is scrolled so that only the n last lines are visible. The input text is buffered until the enter key is pressed, so the application receives a random string of text. In this mode, the application needs not know much about the terminal. For many interactive applications, this is not sufficient. One of the common enhancements is command line editing. It also may give access to command history. This is very helpful for various interactive shells. For an application, the simplest way to use a terminal is to simply write and read even more advanced interactivity so that even more advanced interactivity is provided with full screen applications. Those applications are completely control the screen layout, and they also respond to key pressing immediately. This mode is very useful for text editors, file managers, and web browsers. In addition, such programs control the color and the brightness of text on the screen and decorate it with underline, blinking, and special characters. To achieve all this, the application must deal not only with plain text strings, but also with control characters and escape sequences, which allow to move cursor to an arbitrary position to clear portions of the screen, change colors, and display special characters, and also respond to function keys. The great problem here is that there are so many different terminals and terminal emulators, each with its own set of escape sequences. In order to overcome this, special libraries have been created together with the terminal description databases. Unfortunately, the libraries, the databases, and the terminal emulators themselves are too often buggy. So it is not unusual to see them display imperfect or garbled or functional keys not working. In recent years, the general switching of users to graphical user interface GUI has lessened the attention paid to terminal handling libraries and to terminal emulation and almost stalled the debugging efforts. A terminal emulator is a computer program in a graphical windowing system that lets the user operate a text terminal in a window. This lets text terminals coexist with modern graphical user interfaces. Let us now focus our attention on virtual devices. A virtual device is a file that is treated as a device as far as user-level software is concerned, but is generated by the kernel without reference to hardware. It is a device simulated by the operating system. It is a device file, but does not reference any hardware. Examples of such devices are null in Unix operating systems and null device in DOS, Windows, and OS/2 operating systems. Device files often provide simple interfaces to peripheral devices, but they can also be used to access specific resources on those resources or on those devices. They are useful for accessing system resources that have no connection with any actual device, such as data sinks and random number generators. Alternatively, referred to as visual peripheral, a virtual device mimics a physical hardware device by tricking the computer into thinking something exists when it really doesn't. For example, fax software can act as a visual printer. When the print is selected, the document is sent to a fax modem, which then sends information to another fax modem or fax machine instead of a printer. For instance, when "-dev "-null is written to, the kernel tells the program it wrote everything to it without actually writing it anywhere. And when read from, the reading program is told that it has reached the end of the file. A virtual disk image is a file on a physical disk which has a well-defined, published, or proprietary format and is interpreted by a virtual machine monitor as a hard disk. A virtual device or a virtual drive in computing is a device that to the operating system appears to be an ordinary physical disk drive with disk images substituted for disk reading hardware through the use of software that is called a disk emulator. A virtual device driver is a program that handles software interrupts from the operating system rather than hardware interrupts for devices, including the hard disk drive controller as parallel ports. It is used with a device that has changeable settings. In open systems, a virtual terminal, VT, is an application service that hosts terminals on a multi-user network to interact with other hosts regardless of terminal type and characteristics. Number 2, allows remote log on by local area network managers for the purpose of management. Number 3, allows users to access information from another host processor for transaction processing. Number 4, serves as a backup facility. In open systems, a virtual terminal, VT, is an application service that performs the functions that we have already looked at. That is, allowing host terminals on multi-user network to interact with other hosts regardless of terminal type and characteristics, allowing remote log-on by local area network managers for the purpose of management, allowing users to access information from another host processor for transaction processing, and serving as a backup facility. So what are the main advantages of virtual devices? Number 1, there will be no need to have a second system while testing the operating system. Number 2, all generic hardware found in other PC will be provided by the virtual machine. Number 3 is more enhanced user experience. Number 4 is very good quality of service. Number 5 is that virtual devices can complete several works at a time without creating pressure on the system. Kernels provide many services that are related to I/O. These services include buffering, caching, and spooling. Let's commence with looking at buffering. Buffer memory is a temporary storage or holding place for data that is moving to or from the central processing unit or from either the input or output devices so as to set the CPU free to carry out other activities during processing of data. This is because the CPU is very fast compared to other devices. It acts as an interface between very fast processor and slow I/O devices. A buffer is a temporary memory location that stores data while they are transferred between two devices or between a device and an application. Buffers are used for many purposes, such as 1. Interconnecting two digital circuits operating at different rates. Number 2 is holding data for use at a later date. Number 3 is allowing timing corrections to be made on a data stream. Number 4 is collecting binary data bits into groups that can be operated on as a unit. Number 5 is delaying the transit time of a signal in order to allow other operations to occur. Buffering is done for 3 main reasons. Number 1, to cope with a speed mismatch between the producer and the consumer of a data stream. The buffer provides a waiting station where data can rest while slower device catches up. A buffer is traditionally used because CPU instructions can directly address data that is stored in peripheral devices. Thus, addressable memory is used as intermediate stage. Number 2, to adapt between devices that have different data transfer sizes. A buffer may be feasible when a large block of data is assembled or disassembled as required by a storage device, or when data may be delivered in a different order other than that in which it is produced. Number 3 is to support copy semantics for application I/O. A whole buffer of data is usually transferred sequentially, for example, to hard disk. So, buffering itself sometimes increases the transfer performance or reduces the variation or jitter of the transfer's latency. What is caching? A cache memory or a cache memory is a small high-speed static RAM that is incorporated in most modern microprocessors and motherboards in order to allow the processor to access data and instructions much more quickly, especially that which is accessed most frequently. A cache memory is a memory that is smaller and faster than main memory, and that is interposed between main memory and the processor. Such a cache memory reduces average memory access time by exploiting the principle of locality. Cache is a component that improves performance by transparently storing data such that future requests for that data can be served faster. The data that is stored within a cache might be values that have been computed earlier or duplicates of original values that are stored elsewhere. Nevertheless, caches have proven extremely effective in many areas of computing because access patterns in typical computer applications have locality of reference. References exhibit temporal locality if data is requested again that has been recently requested already. References exhibit spatial or spatial locality if data is requested that is physically stored close to data that has been requested already. Hardware implements cache as a block of memory for temporary storage of data likely to be used again. The CPUs and hard drives frequently use a cache, as do web browsers and web servers. When the cache client, for example, a CPU, web browser, or operating system, needs to access a data presumed to exist in the backing store, it first checks the cache. If any entry can be found with a tag matching that of the desired datum, the datum in the entry is used instead. This situation is known as a cache hit. The hit rate of a cache describes how often a searched for item is actually found in the cache. More efficient replacement policies keep track of more usage information in order to improve the hit rate for a given cache size. The latency of a cache describes how long after requesting a desired item the cache can return that item when there is a hit. Faster replacement strategies typically keep track of less usage information, or in the case of different or direct mapped cache, no information to reduce the amount of time required to update that information. The percentage of accesses that result in cache hits is known as hit rate or hit ratio of the cache. The alternative situation when the cache is consulted and found not to contain a datum with a desired tag has become known as a cache miss. The previously uncached datum fetched from the backing store during mishandling is usually copied into the cache ready for the next access. In a write-through cache, every write to the cache causes a synchronous write to the backing store. Alternatively, in a write back or write behind the cache, writes are not immediately mirrored to the store. Instead, the cache tracks which of its locations have been written over and marks these locations as data. The data in these locations is written back to the backing store when those data are evicted from the cache, an effect referred to as lazy write. For this reason, a read miss in a write-back cache, which requires a block to be replaced by another, will often require two memory accesses to service, one to retrieve the needed datum and one to write replaced data from the cache to the store. No write allocation is a cache policy which caches only processor reads, thus avoiding the need for write back or write through when the old value of the datum was absent. Caches are such a good idea that modern CPUs have two of them. The first level, or L1 cache, is always inside the CPU and usually feeds decoded instructions into the CPU's execution engine. Most chips have a second L1 cache for very heavily used data ones. The L1 caches are typically 16 KB each. In addition, there is often a second cache that is called the L2 cache that holds several megabytes of recently used memory once. The difference between the L1 and the L2 caches lies in the timing. Access to the L1 cache is done without any delay, whereas access to the L2 cache involves a delay of 1 or 2 clock cycles. Let us now focus our attention on spooling. Spool is an acronym that stands for Simultaneous Peripheral Operations Online. Simultaneous Peripheral Operations Online. It refers to a process of placing data in a temporary working area from where another process or device can access them when it is ready. Spooling is useful because devices access data at different rates. The most common spooling application is print spooling. When you choose to print a document, the computer sends the document information to the printer very quickly, but the printer can't accept it at the same rate. The printer can only handle a chunk of information at a time, and it pauses to process and print that chunk before it's ready for more. Meanwhile, you have to wait until the printer has accepted the whole document piece by piece before you can use your computer again, because the computer has to hang around and feed the information through. That's why you need a print spooler software that reduces the amount of time during which you can't work while you wait for a job to print. A spooler works by intercepting the information going to the printer, packing it temporarily on a disk or in memory. The computer can send the document information to the spooler at full speed, then immediately return control of the screen to you. The spooler, meanwhile, hangs onto the information and feeds it to the printer at the slow speed that the printer needs to get it. So, if your computer can spool, you can work while a document is being printed. You will notice during spooling, though, that your work gets slightly interrupted for a few seconds here and there because the computer cannot really do more than one thing at a time, meaning it can't keep the spooler running and your monitor running at the same time. So, if your cursor doesn't move or the letters type sporadically here and there, don't worry. Total control will be returned to you when the printer is done. Spooling is a way of dealing with dedicated I/O devices in a multi-programming system. Consider a typical spooled device, the line printer. Although it would be technically easy to let any user process, open the character special file for the printer. Suppose a process opened it and then did nothing for hours. No other process could print anything. Instead, what is done is to create a special process called a daemon and a special directory that is called a spooling directory. To print a file, a process first generates the entire file to be printed and puts it in the spooling directory. It is then up to the daemon, which is the only process having permission to use the printer's special file to print the files in the directory. By protecting the special file against direct use by users, the problem of having someone keeping it open unnecessarily long is eliminated. Spooling is not only used for printers, but it is also used in other situations. For example, file printer over a network often uses a network daemon. To send a file somewhere, a user puts it in a network spooling directory. Later on, the network daemon takes it out and transmits it. One particular use of spooled file transmission is the Usenet network, which is primarily used as an electronic mail system. This network consists of thousands of machines around the world communicating by dial-up telephone lines and many computer networks. Congratulations for viewing and listening to this video on computer clock system, computer terminals, and virtual devices, which is part 5 of 5 in device I/O management topic. You can listen to the other parts of device I/O management topic, as well as other videos in the field of computers versus ICT from MLSwap ICT YouTube channel. In addition, for you to be able to access free life skills, motivational, and inspirational resources, visit MLSwap Motivation YouTube channel. I would also request that you subscribe to both channels by clicking on subscribe button once you are in the channel in order to receive immediate updates whenever a new video is posted. In case you have any questions, suggestions, or recommendations, you are free to communicate with us or write to us through the email mlswap@gmail.com. Thank you very much for listening to me and be blessed.